Let's talk about another important topic in statistics, which is significance testing. Sometimes you'll hear this idea thrown about with the words statistically significant. We're going to ignore that terminology, and instead we're trying to be a bit more precise and guide things more in terms of the concepts of probability, and we're going to give you a framework for understanding what people mean when they say that. So recall that in binary hypothesis testing, we were given, or we had two hypotheses that we called H0 and H1, and we had an observation Y that was generated either by the conditional probability of Y given H0 or the conditional probability of Y given H1 in the continuous case. And for everything we're going to say today, we're going to stick with the continuous case. Okay, we were using Y then to decide whether or not H0 or H1 occurred. Okay, one way we could do that is we could use the ML rule, and we decided H1 if the conditional probability of Y given H1 was greater than or equal to that of Y given H0 for the particular value of Y that we observe, and if Y given H0 was larger, then we picked H0. So the difference here in significance testing is really that we're only going to have an explicit probability model for what we're going to call the null hypothesis H0. Okay, so we are only going to have f of y given H0. We are not going to have f of y given H1. So these are going to be our choices. We're going to observe y, and based on this observation, we will either reject the null hypothesis or we will fail to reject the null hypothesis. And let me just say a little bit about that language, which you will see used pretty commonly. So rejecting the null hypothesis is kind of like what we were doing in the ML rule when we decided H1, because we're not deciding H0 here, meaning that we're rejecting the null. Okay, so that kind of makes sense. So why say fail to reject the null instead of accept the null? Well, the whole idea here is that we really just don't have a rich enough model to know whether the null has occurred or not. So we're trying to couch that in this language which conveys the fact that we don't have a full probability model. So either we're rejecting the null, we're saying it doesn't make sense that it was the null hypothesis, or we're saying we have not gathered enough evidence to reject the null hypothesis, so we fail to reject it, rather than saying we accept it. So that's how people often refer to it. I just wanted to use that language so that you're familiar with it. Okay, let's look at some examples and maybe it'll be a bit more clear. So let's say you're trying to design a good website and you deploy an A version to certain users and a B version to other users. Maybe that involves differences in colors, button shapes, whatever you like, okay? And what you do is you measure the click-through rate, so how often people click into your website, based on which website they're seeing, the A version or the B version, okay? And your null hypothesis is that it doesn't matter, meaning that the average or mean click-through rate will be the same for the A version and for the B version. And you'll often hear this idea called A/B testing. Here's another example. We're going to administer a new drug, so we're testing a new drug, and we're going to give it to a group of patients. And a different group of patients, we're going to give a placebo. We'll call them the control group. And the null hypothesis in this case is that their mean cholesterol levels will remain the same. So if you look at the cholesterol level at any given individual, it's going to be some value, but the average within the group which you're trying out this new drug might be different than that where you have no drug and you just have a placebo. So the null is that it doesn't matter, the drug isn't doing anything, and the mean is the same. And if you reject the null, you're saying that the mean would be different. As a final example, let's say that you change the reactor temperature when you're trying to manufacture some product, and you measure the yield that you get before and after this change. And your null hypothesis here is going to be that the mean or average yield is the same regardless of the two temperatures. Okay, so meaning that the temperature change did not affect your yield. And if you reject the null hypothesis, you're saying that the mean did in fact change. All right. So let's be a little bit more precise. So what we need to do is construct some kind of significance test. And we're going to do that with something we're going to call a significance level, alpha. And I'll say what that means in a moment. To do this, we select a rejection region, R0. And what this means is that we want the probability that y falls into R0 under the null hypothesis H0. We want that probability to be alpha. Okay? So basically, if y falls into the region R0, that's where we're going to reject the null hypothesis. That's our rejection region. If we integrate over that region, the conditional probability of y given H0, that should be alpha, meaning that the overall probability conditioned on the event that the null did occur should be alpha. Okay, so to be precise, so if y falls into this R0, we're going to reject the null. And if y does not fall into R0, we're going to fail to reject the null hypothesis. Okay? And remember, we're doing all of this using only this one object, f of y given H0. There's no f of y given H1, and there's no probability of H0, and there's no probability of H1. There's really just this one null model. Okay. So what does this kind of look like in practice? Well, in practice, what we tend to do is rely on some kind of threshold tests. And you'll notice that here we're really limiting ourselves to scalar observations. And so for a scalar observation, we're just deciding whether it's above or below some threshold. So a one-sided test on the right tail of a distribution looks like this. You reject if your value is too high. So there's a high threshold, TH, and when you're in the region where y is above that high threshold, you reject. So here's a distribution. Here's the threshold. And we're going to pick this threshold so that the probability y is greater than the threshold under H0 is alpha. So this area that we calculate should be alpha. We can do the same thing for the left tail. Okay, so we can have a one-sided test on the left tail of a distribution. So we have a low threshold. When we're below the low threshold, that's when we reject. And we want that area to be alpha. So we're going to select this threshold so that the probability y is less than this threshold under H0 is going to be alpha. So one way to think about this is that we're basically saying we're rejecting on one of them if the value is too high, and the other one if it's too low. And we can do it either way. So we can have a two-sided test where if the value is too low or too high, then we reject it. And so then we have a too low value and a too high value, and we're going to select them such that the area on the left side is equal to the area on the right side. This is just a convention, and that it's half of the significance level, alpha over 2. So the left tail is alpha over 2, the right tail is alpha over 2, and when you add those up, you get the significance level that you want. Okay, so basically what this is saying is that, so the way to think about this intuitively, I'm just going to say this, and we're going to say it again, is that the significance level is basically saying that if you have a low significance level, let's say 0.05, then it's unlikely, given that the null is true, that you would have observed that value of y, okay? And so since it's unlikely that you would have observed that value of y under the null, then maybe you should reject that the null is true because it doesn't do a good job of explaining your observation. So also in practice, what people tend to do is instead of computing these thresholds, T low and T high, explicitly, and how would we do it explicitly? We'd have to use an inverse of a CDF. So if we had the CDF, we'd invert it. Usually what you might do instead is compute something called a p-value. And then what you'll do is reject the null hypothesis if your p-value is less than your significance level. Okay, so this is actually a lot easier to do practically. Okay, so the intuition here is the p-value. That's going to be the probability of observing a value at least as extreme as the observation that you've gotten under the assumption that the null hypothesis is actually true. Okay, so what you're doing here is you're saying, okay, I've observed y, and now I'm going to give the null hypothesis the benefit of the doubt and say that it's true. What's the probability that I would have actually observed y or something even crazier than y, whether that means it's larger or smaller, but something that's more extreme. What's that probability? If that probability is really small, smaller than the significance level that I've set, then I'll reject the null. I'll say, based on my significance level, I don't think that the null does a good job of explaining my observation, so I'm going to reject the null hypothesis. The p-value is not the probability that the null hypothesis is true. We have no way of calculating that. It is only the probability that given that it's true, it generated an observation like the one that you've seen. Okay, how does this translate into the test that we talked about? Well, if we have a one-sided test with a right tail, then we have the observed y, and the p-value is just 1 minus the CDF there. So it's, again, the area on the right, and we call the area on the right the p-value. Okay, so we calculate this p-value, this area, by plugging into this CDF, really 1 minus the CDF, and if the p-value we get is less than alpha, then we'll reject the null. We can do this the same on the left tail. So we could compute the p-value by plugging in our observation and computing the integral all the way up to that using the CDF, so the area on the left. That would be the p-value for the left tail test. And for a two-sided test, it's a little bit more complicated. The p-value would be 2 times the minimum of the left area and the right area. Okay, so you get an observation and you compute the area to the left of that, the area to the right, and then you say that the p-value is 2 times the minimum of the left area and the right area. So you figure out which area is smaller. In this case, in this little drawing that I made, the right area is smaller. And remember that our significance level was basically setting that to be alpha over 2 when we were doing it in the other calculation. So the reason we scale by 2 is to kind of match that divide by 2 that we had there. It's not important to be able to derive that. I'm just giving you some context. Okay, so a little bit more on how this is dealt with in practice. So usually we will just rely on some standard test statistics. So all of the stuff that I told you, you won't have to use it necessarily to derive your own tests from scratch, okay? So that's just to give you some context for where these things come from. You can just draw on a standard test statistic. What it's going to do is make some basic assumptions about the data that you've observed. What could be one assumption like that? It could be the family of random variables from which your observation is drawn. So like maybe it's Gaussian or exponential, something like that. So you have some assumption about the random variable family and other kinds of assumptions. If these assumptions are wrong or unreasonable, then everything that you're doing will be wrong or unreasonable. So for instance, the p-values that you get, they will not make any sense. They will be wrong too, but maybe you make decisions on them and those will be unreasonable decisions. So you need to be sure that your assumptions make sense, and that's your job. So what we're going to do here is we're just going to consider a few simple tests that are sometimes used in practice. There are many, many others available, right? And it may be the case that if you are thinking of a particular application and you want to use a good test, there might be one out there that's a better match for you than the ones we're proposing, okay? And to run these tests, usually you need a lookup table and better yet, a built-in function from your favorite numerical software platform like MATLAB. You can basically look up most of the CDFs that you need, okay? And a final word, so in practice, you often see that the significance level that you need to cross in order to reject the null, that's usually set to something like 0.05 or 0.01, but there are some disciplines where it's taken to be a smaller number. So let's say you're trying to manufacture some parts and you really want to make sure that you have very tight tolerances, you might actually use a much lower significance level. So it might be 10 to the minus 6, for instance. Okay, so it really just depends on the application you have in mind and what you can actually maintain. Okay, so we're just going to review 4 different tests now, and I'm going to just explain step by step how to run them and do an example for each, and that'll be it. First, we'll talk about the one sample Z test. And so the assumption we're going to make here is that our observations x1 through xn are in fact IID Gaussian. Okay, they have a mean mu and a variance sigma squared, and that's under the null hypothesis. Keep in mind, we're not making any assumptions about what happens if the null hypothesis is not true. We're basically just trying to come up with a way of calculating p-values under the null hypothesis And that's it. And then we use that as our basis for rejecting or failing to reject. Okay, so that's all we're trying to do, propose a null model. And we're going to assume that, the variance of this is known, okay, and the mean is known, okay? So we know the mean under the null model, and we know the variance under the null model. Okay, and the thing that I want to do is I want to test if in the data that I've observed, the mean has changed from this mu that I believe is true. So if the null is actually true, then the mean has not changed. Okay, then the mean is indeed mu. So I'm just trying to determine if the mean has changed. That's the thing I'm trying to look for. So my two-sided test in that case is going to be a four-step process. I'm going to first compute the sample mean for my data. So I'm just going to average my data. Okay, and then I'm going to compute something called the z statistic. So that's z, which is square root of n, sample mean minus true mean divided by standard deviation. The reason that we do this, and I'm not going to show that this is true, but I'm just going to refer you to the lecture notes, or you can work it out on your own. This random variable z turns out to be Gaussian with mean 0 and variance 1 under the null hypothesis, which is nice because then we can use the standard normal CDF. Okay, so the reason to do this scaling by root n, dividing by sigma, and subtracting mu is just to get it to look like the standard normal CDF. That lets us compute the p-value by just taking 2 times phi minus the absolute value of this z that we got. Okay, so again, I'm not going to convince you why this is true, but you could work out that this p-value is exactly equivalent to the p-value definition we had for a two-sided test a couple of slides back. Finally, all we'll do is reject the null if the p-value we get is less than the alpha that we've chosen, and we will fail to reject the null if the p-value is greater than or equal to that alpha. Okay, and now let's do our example. Okay, so this example, by the way, we're just going to do these examples in a very simple way that you could go through and check on your own with a calculator or with MATLAB, but you should have in your head that this is maybe you're trying to make some decisions about whether, you know, a drug lowers cholesterol level or a website change makes sense and things like that. So you can come up with your own reasons for where this data came from, but we're not going to give that here. Okay, so all we're going to do is apply this one sample z test. Okay, our goal is going to be to see if the mean here has changed from a known value of mu equals 3. So we believe the mean in the null is 3 and the variance is going to be 4. And we're going to set our significance level to 0.05. Okay, so then here's going to be our observations. I'm going to get 5 observations. I'm going to compute their sample mean, the z statistic, and then 2 times phi minus the absolute value of z. That's going to be our p-value, and I'm going to make a decision. Okay, so that's what we're going to do. We're going to do this twice just to get used to it. So let's say I collect some data set. My data set is 4.1, 6.7, minus 1.5, 4.7, 3.6. So the sample mean is 3.52. You can work that out on your own. So now I'm going to go and plug that into that z statistic. And I know that n is equal to 5 here. So I have root 5 times sample mean 3.52 minus 3 divided by root 4, because that's the square root of the variance is the standard deviation. Works out that this is 0.58. Now I'm going to plug in 0.58 into 2 times phi. I'm going to have minus 0.58. If I do that, and I can use MATLAB to do that, I'm just going to get 0.56. That's greater than my significance level alpha, which is 0.05. So I, in this case, will fail to reject the null. Okay, and if you've already forgotten what that means, that's basically like saying, for now, we're going to continue to assume that the null hypothesis is true, but this is just a way of saying that, yeah, we're just doing this on a little bit of evidence. We don't have an airtight case here. Okay, let's say someone else wants to repeat this experiment, or they're running a totally different experiment, but they collect a different data set, and they're going to see what conclusion they reach. Okay, so there's a different data set now, and maybe it's collected by a different lab in a different place. You can't combine the data sets. So you have 5.0, 6.1, 5.5, 3.4, 4.6, and 4.92 as your sample mean. Okay, so you can work out that that is the sample mean for those values. Again, you're going to have root 5, 4.92 minus the mean 3 divided by root 4. That works out to be 2.12. When you plug this in to 2 times phi minus absolute value of z, you get 0.034, which is less than 0.05. So in this case, you reject the null. What does that mean? It means that you do not believe that the null distribution, which is that the data was IID Gaussian with mean 3 and variance 4, explains the data according to this significance level of 0.05. Okay, let's make things a little more interesting. This is the one sample t-test. We're going to keep the same assumptions about Gaussianity. So we're going to assume that our observations x1 up to xn are going to be IID Gaussian with mean mu and variance sigma squared under the null hypothesis. And we're going to assume we know the mean, but we do not know the variance. Okay, so the variance is not known to us. There is a variance, we just don't know it. And we want to test now whether the mean has changed. Okay, so we want to do the same thing as before. We have a mean under the null, and I just want to check whether or not it still holds. I'm going to run a two-sided test with 5 steps now. So my 5 steps are going to be the following. So first, I'm going to compute the sample mean. So I'm going to average my data. And now I need to know the variance. So I'm going to actually have to compute the sample variance. Okay, so I'm also going to do that, get this Vn. Okay, remember I have this 1 over n minus 1 normalization factor that we had on the previous video. Now I compute the t statistic, which is t square root of n, sample mean minus true mean, square root of sample variance, because I don't know the true variance. This turns out to have a t distribution with n minus 1 degrees of freedom under the null. Okay, I compute the p-value, and this f of t is the CDF of a t distribution with n minus 1 degrees of freedom. Okay, and I can look up that using a lookup table or my favorite numerical computing package. The way that I compute the p-value is I just take 2 times this CDF and then plug in minus the absolute value of the t statistic that I got above. And finally, I have my p-value, so I'm going to reject the null if the p-value is less than alpha, and fail to reject the null if my p-value is greater than or equal to alpha. Okay, we're going to do another example, this time just one data set, and I'm going to apply this one sample t-test. Okay, so this is the test that I've chosen to use. And what I want to do is I want to see if the mean has changed from what I believe it is under the null. Okay, so I want to see if it's changed from mu equals 2. I don't know the variance. And I'm going to set my significance level to 0.05. Now, I'm also assuming tacitly, since I'm using this one sample t-test, that under the null x1 through xn are IID Gaussian. If that assumption isn't valid, then this is a bad test. So x1 up to x5 are going to be my samples. I'm going to compute the sample mean and sample variance, the t statistic, my p-value, and then I'm going to make my decision. Okay. So I'm going to get 0.3, 1.9, 1.8, 2.3, 2.4, and 1.74 for the sample mean, and 0.71 for the sample variance. So I have 5 data points. So my t statistic I get by taking root n, so that's root 5, sample mean minus true mean, divided by square root of sample variance. When I plug this in to the t distribution CDF, and the way that I've done that here is I plugged in MATLAB to this function tcdf minus 0.694, right? Why did I use 4? Because it's n minus 1 degrees of freedom. I have 5 observations, so n minus 1 is 4. I get 0.26. That's greater than alpha, so I fail to reject the null. All right. Okay, now let's look at a 2-sample test, starting with the 2-sample z-test. The idea here is now I'm going to have 2 data sets, x1 up to xn1, y1 up to yn2, okay? Meaning that the size of these data sets may not be the same. The way to think about this is maybe I've collected data in different circumstances. That could be that I had a treatment group and a control group. It could be that I have users visiting an A website and a B website. But I have 2 different data sets. And under the null hypothesis, I'm assuming that x1 up to xn1 is IID Gaussian with a mean mu1 and variance sigma 1 squared, and y1 up to yn2 is IID Gaussian with a mean mu2 and variance sigma 2 squared. And so the mean is the same under the null. So I'm assuming under the null hypothesis, the groups or the data sets have the same mean. They don't have to have the same variance, but they have to have the same mean under the null. But I don't know the means. I just think that they're the same, but I do know the variances. I know sigma 1 and sigma 2. Okay, and what I want to test is whether the means are now different. Okay, so under the null hypothesis, the means are the same, and I want to check whether my treatment actually makes a difference, meaning that the means have become different, or whether one website is better than the other, meaning that the click-through rate is different on average. Okay, I'm going to do this with the 4-step two-sided test. Okay, the first thing I'm going to do is compute both sample means. All right, so I'm going to have mn1 1 and mn2 2. Okay, and then I'm going to have the z statistic as before, but I'm going to compute it in a slightly different way. I'm going to take the difference of the sample means and divide it by this object, which is a normalized version of the variances. Okay, so why exactly to do that is just to make sure that under the null distribution, this statistic looks Gaussian with mean 0 and variance 1. And why that's true, you can look at your lecture notes for some reasoning. We're not going to show that here. All we're going to do is just note that this is just a particular statistic I can calculate. I know the sample means, I know the exact variances, and I know the sample sizes, so I know n1 and I know n2, so I can work out the z statistic, and I know that it's going to be Gaussian 0, 1 under the null. That means it's easy for me to compute the p-value. It's just 2 times phi minus absolute value of the z statistic, and I'll reject the null if the p-value is less than alpha, just like usual, and I will fail to reject the null otherwise. Okay, and so I'm going to just use this in an example, all right? And so in my example, I've collected 2 data sets, and I'm going to use the 2-sample z-test to determine whether I think the means are different, okay? So if the means are different, I'm going to reject the null. All right, and I'm going to assume that I know the variances, so let's just say the variance in one case is going to be 1, and in the other case it's going to be 2, and I'm going to set my significance level to 0.05. Okay, these are my sample indices, all right? So these are basically the indices of the data points I've collected. So if it were, so it could be x1 up to x5 or y1 up to y5. This is going to be my sample mean value. And I'm going to have my z statistic, my p-value, and my decision. Okay. So I'm going to have my data set from x, okay? And from that, I'm going to observe some values, and I'm also going to have a data set for y. And so data set for x is going to be 4 values only, okay? So it's 0.1, 1.0, 0.8, 1.6, and then nothing. So the size of my data set is 4 points, not 5 points. Y has 5 points. They happen to be 2.7, 4.6, 1.5, 3.0, and 3.8. Now, on a first glance, these do look pretty different, right? So it seems like y is getting higher values than x, but keep in mind, y also has higher variance. So let's use this test to determine whether or not we should reject the null. The sample mean for x is going to be 0.88, and for y it's going to be 3.12. The z statistic will be 0.88 minus 3.12 divided by the square root of 1/4 plus 2/5. Okay, so that's going to be the variance of the data from x, which is 1, divided by the number of points in x, that's 4, plus the variance for y, which is 2, divided by the number of points in y, which is 5. Take the square root of the whole thing. This works out to be minus 2.78. When I plug this in, I get a really small number, 0.0054, which is less than alpha, so I reject the null. Finally, let's look at the 2-sample t-test, and that's going to have the same setup as before. We're going to say that I have 2 data sets. They might be of different sizes, n1 and n2. And under the null, we're again assuming that everything is IID Gaussian. Okay, so x1 up to xn is IID Gaussian. It has a mean mu1 and variance sigma 1 squared. y1 up to yn2 is IID Gaussian. Again, mean mu2 variance sigma 2 squared. And they have equal means under the null and variances. Okay, so you might think that in the previous test, the z test, we were allowed to have different variances. Here it's a little trickier. So we're going to actually set them to be the same for now. Okay, the thing that we're going to assume is that the means and the variances are all unknown. So I don't know the means and I don't know the variances. But under the null, I believe that they're both the same. So the means are the same and the variances are the same. And what I'm trying to test is whether the means are now different. Nothing about the variances, I'm just testing if the means are different. The way I'm going to do this is I'm going to compute the sample means. Okay, so I just average my two data sets, and then I'm going to compute my sample variances, okay, because I don't know the variances either. So I compute them for my data sets. Remember, I normalize by n1 minus 1 and n2 minus 2 because of this desire to have an unbiased estimator. And then I'm going to compute this kind of pooled variance estimator. So I put these two sample variances together in this particular way with this formula. Okay, so the reason to use this formula, why exactly to use this is, again, not super important. All I'm trying to do is put together my data from X and from Y to get an estimate of my variance, which I believe to be the same. So it's okay to combine the data to estimate the variance. Okay, so what I'm now going to do is compute the t-statistic. The t-statistic is going to take the difference of the sample means, divide by this sigma hat, and then multiply by the square root of 1 over n1 plus 1 over n2. It turns out under the null distribution, this has a t-distribution with n1 plus n2 minus 1 degrees of freedom. Okay, we can use that fact to compute the p-value. Okay, the p-value is just plugging into the CDF minus the absolute value of the t-statistic and multiplying by 2. And this CDF is from a t-distribution with n1 plus n2 minus 1 degrees of freedom. And we reject the null if the p-value is less than alpha, and otherwise we fail to reject the null. Okay, so what if the variances are unequal and unknown? So of course there are ways to deal with this. They're just a little beyond our scope. So one option you might see out there is to use something called Welch's t-test. You could look that up. It's beyond our scope. Okay, finally, let's compute an example. So I've kind of just pushed this two-sided test steps for the two-sample t-test up. And what I want to do is apply the two-sample t-test to see if the means in two data sets are now different. Okay, and I'm going to make this assumption, so I'm tacitly making this assumption that the variances are unknown, but they are the same under the null. Okay, so my significance level is always 0.05. Okay, so I'm going to get this first data set from X, which is going to be 4 points. I'm going to get its sample mean and its sample variance. So I get 3.6, 0.4, 2.1, 3.7, compute sample mean 2.45, and sample variance 2.4. Y, as before, we're going to say is 5 points. Okay, so just to keep it contained, we're just having a difference of one data point, but just to show you that they can have different numbers. So 10.2, 8.5, 0.3, 9.1, 4.5, 6.52 for the sample mean, 16.72 for the sample variance. Okay, so there's quite a bit of difference there. So I can now put these two things together, right? So I'm going to get my sigma hat here. So I get n1 minus 1, so 4 minus 1 times the sample variance, plus 5 minus 1 times the sample variance for the second data set, divided by n1 plus n2 minus 2, so 4 plus 5 minus 2. This works out to be 3.25. So my t-statistic is the difference of the sample means, 2.45 minus 6.52, divided by this sigma hat, which is 3.25, times the square root of 1 over n1, which is 4, plus 1 over n2, which is 5. That's the number of points in each data set, 4 and 5. If you go through this, you get minus 1.86. Okay, so I'm going to plug in to the CDF for the t-distribution to get my p-value, right? So I plug in minus 1.86, and I'm going to use MATLAB to do that. So I'm going to call tCDF, and the value I'm going to put in here is 8. Why do I put in 8? Because 4 plus 5 minus 1 is 8. Okay, and that's the number of degrees of freedom. Okay, so I get 0.099, and that's greater than my alpha just by a little bit, but I still fail to reject the null hypothesis. So what this is saying basically is, yeah, it is possible to observe something like this under the null. It's maybe not the most likely thing, but it's above our significance level. And the way that we've decided to do this before running our experiment is that we're going to fail to reject the null, meaning that we still think, there's enough evidence around to hold on to the null for a while. And the main thing I'd caution you about is before running around and trying to apply this to every data set that you see is you really do want to sit down and try to think through what are the ramifications of using this kind of process, what are the statistical fallacies you can run into, and there's a lot of interesting literature that's emerged on that. So I don't think that this is something that you should just apply blindly, but it is a very useful tool, and it is something that you'll see used very often in science and engineering. So it's a good thing to learn about.